Okay, so to start, was there any questions about the quiz? Project 1 we saw is due next Monday. I sent an email out. Next Wednesday, I'm sorry. That's when the project will now be due, because I know a lot of us were going to be gone. And this weekend I would expect you to work on it, so hopefully you can work on it next week. On the quiz, I noticed a lot of us in that first quadrant, if you have it back, you should be able to see it, but in that first quadrant with force number 1, we were switching sine and cosine, and I'm not positive why, because not positive WHY in this class. But that 60 degrees, was it? That's on the x-axis, so it is correct to use cosine for x, sine for y. I think I had about a third of you guys switching it and using sine for x, cosine for y. So if that's still pretty confusing for you, make that whole triangle, fill out f1x, f1y, see what's opposite, see what isn't, and then use cosine, sine, fully do those equations and fill them in appropriately, okay? If you're comfortable enough that that's not something that you have to do, then let's start skipping those steps. Okay, we don't need to write out every single step of sine. This is what sine means. This is what I'd plug in. This is how I would divide over, okay? If you're comfortable enough with it, start skipping. If you have questions on the quiz, please ask. It is under quiz 2 in the grade book, because when you guys turned in that random sheet of paper the first time we met with the Cartesian vector on it, I wanted that to be quiz 1 and that kind of help out your quiz grade. So I'll have that in the grade book this afternoon, but this last quiz was under quiz 2, and then the next one we have will be quiz 3. So fair warning when you look at the grade book, okay? Quizzes are worth about 10%. I'm really testing what you're picking up during lecture, so that's how they'll always be, usually just one problem. I'll post it up on the deal. I can watch y'all take the quiz. When I'm not here, a seat in between all of you, just a piece of paper and pencil and calculator will be it. So let's jump into the lecture. I had been watching some YouTube videos about how to better explain moments clockwise and counterclockwise rotation. I feel like I do struggle with that in this class, and it's always my goal to explain it to you as easily as humanly possible. So I feel like I do not do a good job with that. So we're going to start off doing some more problems on moments, and then we'll go into like the next section of our lecture, which isn't too bad once we have moments down. That'll be a little bit easier. But I wanted to start off with this problem that says determine the resultant moment about A, B, and C. Okay, so here's A over here. That's a little pin connection. Here's a roller connection that they're calling B. And then I'm going to call C up here in the corner. And what I want us to see is how torque is affecting this beam at different points. If we were to analyze different points along this beam, what is the torque at each one of those points? Okay, but something that I saw in one of the YouTube videos is when we're thinking about clockwise and counterclockwise rotation, let's say that this is A, we're going to act like whatever member that we are analyzing is going to be the clock hands of a clock. And if we put that point that we're analyzing, so this first one we'll just be doing A and then B and C on some other slides. But if we're just doing A becomes the origin or the center of the clock. And when we break down different forces, then we should be able to see if we had one string connected from the middle of the clock to the middle of my force, which direction would it go if it was in motion. Okay, so hopefully that clears things up a little bit. I know that I'm going to have to divide this force up. I'm going to call this one F1 over here, or this guy F1, and then this one F2. So I'm going to have an F2Y and an F2X. And what are those magnitudes? It would be 15 3/5. And so that is, and then we would have 15 4/5, and that is what? Oh my gosh. Pull it. 12 kilonewtons and 9 kilonewtons. Okay? So then once we break down every single force, we're figuring out the moment for every single force. So we go back through, we have all of our force equations, okay? When we're looking at this beam, what we've done in the past couple of weeks is not negated. We're just moving past that a little bit, just doing moments right now, okay? Next week, we'll start to combine both a force analysis, finding a force resultant, and a moment resultant, all in the same problem. But for now, we're just figuring out how each one of these forces is creating torque, okay? But there is still force going in the X, force going in the Y at all these different magnitudes that we do need to keep in mind. Okay, so I'm going to start with my F1, and I'm going to say my moment, this is the end goal, is the sum of all the moments about A. That's what we're looking for in this problem. M of, I wanted to do another M, F1, we would get 20 kilonewtons, okay? Sign does not matter, it's just the magnitude of that force. And then its distance, correct? And from A to F1, how far is that? 2. I'm gonna plug in kilonewtons here. Okay, and then we look back at it and say, is it going clockwise or counterclockwise? So looking down at our clock, we are going, yes, clockwise. It is going in the direction that the clock would. So we're saying clockwise for that one, okay? And then I'm gonna have M, F2X, and that one is 12 kilonewtons. And that distance needs to be a distance in the Y because it's a force in the X, and it can be from that line of action all the way back to A. So what is that distance from F2X's line of action back to A? Okay, so if we did 6, it would be this distance here. That's what you're thinking, right? And then it's this distance here. So does this line of action and this distance correlate to one another? No, because that force is moving in the X, and that distance is not the perpendicular distance from A to F of X. They don't even touch each other. They never will touch each other. That line of action. Yep, so it's just 2. It would be 2 meters there. Okay, back to the clock. Would that F2, if it was tethered from here to here, and then set to spin, or set to move, there's a motor in the back of the arrow, which direction would it be spinning around that clock? Yes. Okay, so it would be headed this way. MF2Y, we would have 9 kilonewtons, and then we would use which distance? Six. So we have to go all the way back to A. And then what is that distance from this one's line of action? There we go. That's my perpendicular distance. That's what I'm looking for, and that's what I have, which is 6 meters. Which is 54 kilonewton meters. And would that one be going clockwise or counterclockwise? Counterclockwise. Okay, so if I do the sum of all the moments acting about A, I'd get negative 40, negative 24, plus 54. So I'd get negative 10, and so that is what? 10. Okay. Good. To move on to the next one? Yes, go on. Why is it negative 40? Because we're talking about this force here. Okay, we had a distance of 2, the magnitude was 20, and if we let that arrow go, it would swing around clockwise, making it negative. Okay, so I'm taking all of these and I'm summing them straight up in this equation here. Okay. So let's do the same problem, but now taking the resultant moment about B. So about the roller, how does this change things? Okay, so now our origin is going to be set up about B. We are going to have the same force, right? This force does not change. We had 9 kilonewtons here, and 12 kilonewtons here, and then 20 kilonewtons here. Okay, but now the rotation about B does change. So if we had moment of F1, which we're saying is 20 kilonewtons, what is that distance back to B? 2. Okay, where do we see 4? Nope, now the origin is B. So right here, that is B, right here where the roller is. 2. Okay, now is that one going clockwise or counterclockwise from B? F2x, we have 12 kilonewtons. And what's that distance? Still 2. And is it going clockwise or counterclockwise? And then we'll have F2 in the y direction. And we've got 9 kilonewtons. And what is it to get from B? It's got to be in X direction to get to that line of action of 9. So that distance is? Yes. So now we have 18 kilonewton meters going clockwise or counterclockwise? So we get a positive 40 now, negative 24 plus 18, giving us 34. Okay, always remembering our clockwise or counterclockwise. The sum of, I'm always going to put what point I'm analyzing about, if it gives me that, or ask me for one. Okay, yes. Yep. Do not put negative and clockwise. You're only using clockwise and counterclockwise. Okay? So the idea of this one is just to see how that torque varies based off of what position you are at on the beam. Okay, so if we're going to say C here, now our clock looks like this, right? Here is our C. We still have 12, 9, and 20. So if I did my moment from force 1, I would have 20. And what would my distance from C? This force is in the y direction, so I need an x distance. What would be that distance? 4. And is it moving clockwise or counterclockwise? About C. Counterclockwise. Okay, so this one, if let go, this is how it would go about the clock. And then MFX, F2X. We have 12. Did we have 12? Yes, I messed those up. Here and 9 is there. So we would have 12, and what's the distance from C to F2 of X? From here to C? What would be that distance? 0. There is no distance, okay? If that line of action at any point can pass through whatever point we're analyzing about, there's no distance. What happened there? Okay, and then what about F2Y? Yep, same thing. The line of action passes right through C, meaning no distance. And so my sum of the moments about C is just going to be 80, right? That's all there was. It was just that 20 kilonewtons acting on that beam. Okay? Does that kind of clear things up? The clock may or may not. It was my first go at. Okay, questions?